Okay, hello everyone. So I will now go over discussion section 3 worksheet and their solutions. So let's start with the first question, the MDPs. We look at question 1, we're given this MDP that we see here. And then the first part asks us, suppose that the maximum horizon length is 15. What would be the optimal action if the discount factor is 1? So meaning you don't care about ever losing reward. Always the rewards are going to be equal to you. So intuitively, let's look at this MDP here. Even in our worst case scenario, if we're at B, we would want to go towards F because given 15 steps, we're still going to get a maximum utility of 11 if we go from B to F. Whereas if we went from B to A, we would only get 10. So let's take a look. If we were to follow that intuition, what would be the best action? We would just try our best to head towards F, right? And then loop inside the F reward for as long as possible. So writing that down, if I were in A, I kind of can't do anything. Then I have to go back towards A. And it's better if we are at B, C, D, E, or F. Then we have the option of heading towards F and achieving that maximum utility. So if B, we would head towards C. For C, we would head towards D. For D, we would head towards E. And for E, we would head towards F. And for F, we would loop back to F to get that reward. Okay, so now that we have that intuition down behind us, let's take a look at part B. Suppose now that the horizon is, instead of max 15, so we can only go 15 time steps into the future, we can now go for infinity. We can try to loop as long as we want. So the first part is, does the optimal action depend on gamma? Intuitively, it does, because if we care more about getting reward at once, then potentially if we're really close to the node B, we would want to head towards A. However, if we care less about getting the reward immediately, i.e. having a higher gamma, then we could potentially want to head towards F and loop there for longer. So now let's write down a general equation for how this works. We're going to define two variables. First, let's let this variable n equal to the number of nodes to B. Similarly, let's define a variable n equal to the other place that we can get reward. So remember, we only get reward when we take the action. That's why from B to A, we get that reward. That's why we're counting the number of steps to B. So solving using these two equations, if we were close to B and we wanted to attempt to get the reward at B, the amount of reward that we would see once we go towards B and then end at A, which is a infinite loop, so we can't get out of it, we would have 10 times gamma to the n, because we would get that 10 reward, and the number of time steps it takes to get to that reward would be the power of gamma. Similarly, for m, we have something that's a little more unique because we're iterating infinitely. The reward that we get is, we first get one reward m time steps in the future, then we get another reward m plus 1 steps into the future. Same thing, m plus 2. In fact, this goes on indefinitely, so this is towards infinity. So we now want to see when one would be better than the other, so we want to find a boundary line. Let's begin by calculating that. So we want to find when these two are equal for you at each node. So let's write that down. This right-hand side is a little annoying to evaluate. So let's rewrite this as a sum of infinite, let's write this as the expression of infinite sums. For those of you who remember what this should be gamma to the m over 1 minus gamma. You can review this in either CS188 material or even doing a quick search online will yield you this result. But now that we have this thing, we have a very nice expression that we can solve. So we eventually get gamma to the n minus n plus 10 times gamma minus 10 is equal to 0. So as you can see, depending on what location you are at, different values of gamma will change your policy. Okay, so now we will move on to our next problem, which is our first reinforcement learning problem with MDPs. It's called micro blackjack. In this question, we have a simpler version of blackjack where we have cards that we can get which give us values of 2, 3, 4, 5. And then in our case, we bust after 5. So very small version of blackjack. And using this formulation, let's write out what would our MDP problem look like. So, transition functions. Before we even get to the transition functions, however, I'm going to take into consideration what our actions are. So we have an action which is done, which is to draw. So we have an action which is to draw. And we actually have a second action, which is to stop. Note in this problem, we only actually get the reward if we choose to stop at that point. And drawing itself does not give us any reward, but it potentially sets us up to be in a better state to get reward. So this is very important when we're formulating this problem. But let's start with something simpler. If we are at any transitions, any state, we choose the action to draw. What is the only other state that we can go to? It's done. And this happens with probability 1. We will definitely do this. So we're done with the action. We're done with the action stop. Oh, stop. If we stop, then we will necessarily stop. So we're done with all of our stop actions. Now we just need to consider all the transitions for what happens if we draw. Let's see, what if we are at state 0 and we draw? What state can we end up in? We can end up in 2, 3, or 4 because we could have drawn a 2, 3, or 4. And all of this happens with 1/3 probability. Similarly, we would list out the rest of them. Draw S prime on T3. It would draw any X states. T4 draw. I'll leave this one for later. So for 2, once again, we have 1/3 probability of drawing a 2, 3, or 4, which will put us in our new states, which is going to be 2 plus 2, 4, 2 plus 3 is 5, or 2 plus 4 is going to be 6. So that would leave us into a busted state, which would be done. So 1/3 probability there as well. So let's take a look at what are the next state possibilities for if we were to be in state 3. We can draw a card. So we currently have 3. We draw a 2. Then that would put us in 5, which is good. Or it can put us in done, because if we draw a 3 or a 4, we would end up in done. So the probability of us being in state 5 is 1/3. However, the probability of us being in the done state is 2 out of 3. So we have these situations. Okay, so this is what we have now. What about in 4? 4, if we were to draw, no matter what we draw, we would end up in the done state. Similarly, we would have the value if we were to be in state 5. If we were to draw, no matter what we draw, we would be done as well. So these two transitions are the same. Now let's consider the rewards. Once again, remember, we do not get a reward if we draw. We only get the reward if we stop. So let's write that down. If we're in state S, we stop. Then, and we end up in a new state. We end up in the state done. Then we're going to get the reward of S if it's less than or equal to 5. So similarly, for any other action or state, we're going to get a reward. So similarly, if we choose to do any other action from any other state, we would get a reward of 0. Because the only way we can get reward is if we stop at a state less than or equal to 5. Now, using this information, we want to solve part B, which is value iteration. Before we even get there, let me just real quick write up the update for value iteration. So value iteration, what happens is vk plus 1, so the next value state of a state S is going to be the maximum over all of the actions, of which in our case we have 2, which is draw and stop, so we're going to maximize over these 2 actions, of the expected reward, taking these actions. So I'm going to write it down more formally. So notice that in our case, our gamma is equal to 1, so we're not actually going to care about that. And then the value state is going to, the value that we're going to take is going to be of the next state. Let me write that down better. Okay. Now we start with our algorithm. For our value iteration, we are basically saying if we had k time steps into the future, what is the reward that we can get? So we look at this. If we had no time steps in the future, we cannot do anything. So there's no way we can get any reward. So it's going to be initialized to be all 0. Now, once we have one step, what is the way we need to calculate the value for that? So looking at our equation, we're going to actually do both actions side by side. That way when we take the max, we can take a look at what is happening. So I'm going to keep all the stop actions on the right-hand side and all the draw actions on the left. So if I were to stop at all of these states, I would get the value of the state, right? So that's if I draw, that's if I stop. Whereas if I were to draw, I would get a sum of the probability of transitioning into the new state times the reward, which is none, because we don't get reward when we draw, plus the value of the next state. So if we were in 0, we would go into the states of 2, 3, and 4, all of which in our previous iteration have rewards of 0. So we would have 0 reward here too. Similarly for 2, we have similar situation. It would take us into state 4, 5, and done, which also has 0 in our previous iteration. What about in 3? 0 as well. 4, even more so 0, because we would end up in the different done states. 5 is also 0. Now we take the maximum of the 2 actions. Obviously, we can see that for these 4, our maximum would be to stop. Whereas for this one, it doesn't matter. We can tie break and just say that it stops. Now we have 2 time steps into the future to consider. So we can be like, okay, for all our stop actions, it would still be the same. We would just get the value of whatever state we are at. But now all of a sudden, draw has a different value. So we look at 0. We see that it can end up in states 3, 4, and 5. And in the previous iterations, each of them have actual values now, which is 3, 4, and 5, respectively. We take the average of them. That's going to give us a value of 9 for 2, 3, and 4. So that's going to give us a value of 9, We divide it by 3 because the transition probabilities. And this is going to give us a value of 3. Similarly for here, if we choose the action draw, we're going to end up in states 4, 5, and done. Done is not going to give us any rewards. 1/3 probability of being in 4, 1/3 probability of getting value 5, and 1/3 of getting no reward. This is going to actually give us a new reward of 3. Over here, we can look at it. We're going to end up in 5. We're going to end up in done with 2/3 probability. So this is actually only going to give us 5 or 3 reward value. Over here, this is going to give us a value of 0, a value of 0. So once again, we can find the maximum of the 2. We have new values now for states 0 and 2. Let's continue going. If we have one more iteration, we have 0, 0. Oh, this one's 2. My bad. This is going to give us 3. It's going to give us 4. It's going to give us 5. I'm going to quickly fill in the draw values for 4 and 5 because draw Q values for 4 and 5, which are easy because they only end up in done. This one is going to be the same, it's still 5 over 3. Now over here we have a new value because our over here we can end up in 4 and 5. This is still going to give us 3, nothing special. But it is the 0 that's going to give us a new value because the previous iteration, the 3 had changed. So this is going to give us a new reward of 3 plus 3 plus 4 divided by 3. This is going to get 10 over 3. So now we have updated one more value. In our last step, we're going to actually realize that the final reward is just going to be the same thing as what we calculated above. And thus we see that the values have converged. Now, looking at what we just did previously, it becomes very intuitive because we were keeping track of Q values instead of just the values. So I was cheating a little. But from their Q values, it's very easy to find the optimal policy. We chose the maximum of the Q values. So what was it in state 0 that we did? We chose the draw action. What about in state 2? We chose the action draw as well. What about 3? We stopped. 4, we stopped as well. 5, we also chose to stop. So this is the policy that we would get. Okay, lastly, we are going to take a peek at how we would do policy iteration. So policy iteration consists of 2 steps. The first step is to evaluate our current policy by saying, okay, if we were to follow this policy, what would be the value of each state? And after we evaluate it, we now can iteratively update our policy and then find, using our new value function, the values for each state, what would be the best policy to follow. So let's start with the first step, which is to evaluate our current policy, pi I. So we see that we're going to actually work backwards because it's easiest at state 5. So state 5, we set to draw. Draw would only make us end up in the states done and done. So only make us end up in the state done. So this would end up with value of 0. So without even really calculating, this is going to give us 0. What about for step 4, state 4? If we chose the action to stop, the value that we get from stopping is 4. So once again, no need to calculate anything special. For 3, we would potentially end up in states. If we were to choose the action draw, we would end up in states 5 with 1/3 probability and done with 2/3 probability. So this is going to give us a value of 1/3 the value at 5, which is actually 0. So over here, we would also end up in 0. For 2, we choose the value stop, choose the action stop. The value that would give us is just 2. The value that would give us is just 2. And lastly, for 0, this is something we actually need to calculate because the policy wants us to draw. So we calculate out. V pi I at state 0 is equal to, for draw, we need a sum over all the transition probabilities. And the next states we can get are 2, 3, and 4, right? And then our transition is 1/3 times the probability of we get no reward. This is the value at states 2, 3, and 4. So that's going to be 2 plus 4 plus 0. I'm not going to write it down. This is going to give us, this is going to give us a value of 2. So we can update this. Now we have evaluated our policy. Okay, now we want to somehow update it. And to update our policy, we basically do the exact same thing as what we did previously, which is look at the Q values. So let's go in and start from the rightmost as well, because it's not super difficult. So we want to argmax, we want to take the maximum action, the action that causes the maximum value. So let's look at 5. The actions are to draw and to stop. Now we're considering both actions, not just draw anymore. If we were to draw, we would get the values of the done state, which is still 0, or we can choose the action stop, which is going to give us the value of 5. So the maximum of that would be 5, so the action that is best in this case is to stop. Okay, what about at 4? Similarly, we would only, if we were to draw, we would only end up at the states of stop, of done, which would give us no reward. So the other option is to stop, which would give us a reward of 4. So our best action is also to stop here. So notice up until here, we actually did not use the value functions that we previously calculated from evaluating our policy. So at 3, let's take a look. Do we even use that? So 3, we have to take into consideration if we stop, we get reward of 3. Whereas if we drew, what would be the value that we get? So let me just write it down. Argmax of 3 versus if we were to draw, we would end up in state 5 with 1/3 probability and done with 2/3 probability. The value of 5 is 0. So 1/3 of 0. We would end up with reward 0. We take the argmax of these two values, it would be 3, so the maximum best action is to stop. Similarly for 2, we have to take into consideration the previous values because we can end up in states 4, 5, or stop. 1/3 probability for each. Oh, done. 1/3 probability for each. We take a look at that. That is going to give us a reward of 4/3, whereas the action of just stopping is going to give us a reward of 2. So we see that the best action is actually to stop in this case. Lastly, we consider 0. So this is the one that's slightly more interesting. Before we had said to draw, let's see if it stays that way. If we were to choose the action draw, we would get the reward of being in states 2, 3, and 4. That's going to give us the value of, what was that, 2? 3 is 0, and 4 is 4. With 1/3 probability each, that's going to give us a final value of 2. So that's for draw. Whereas if we were to stop, that would give us a reward, a value of 0. The best one in this case is to draw. And that concludes how to do policy iteration. Note that in the policy improvement step, we actually use the values that we calculated from the evaluation step. Okay, so now we're going to look at one final MDP problem, which is called Grid World Water Park. Looking at this problem, we see that we have this cute little water slide where we get reward if we go down the slide because we're very happy, and it's difficult to climb up, so we get negative reward in that situation. So we start by asking how many deterministic policies are possible in this MDP. There are many states that we can make actions, of which 11 of them we can make choices of going. 2 of them, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The rest of them only have one possible selection. So the number of policies that we have are 2 to the power of 11. 2 of them only have 1, so we have 1 to the power of 2. This is going to give us 2 to the power of 11 total policies. Okay, we're going to look at the next question. I'm going to somehow try to keep that little image still in view. So now we're going to look at part B. So in part B, we want to find the value of what certain states are going to have if we have this many time steps in the future. Remember what the optimal policy, what the optimal value means. It means the amount of reward that we can expect if we have this many time steps to walk. So let's start with our first problem. If we have 3 steps and we start in state A, where the discount is equal to 1, what is the maximum amount of reward that we can get? So we have 2 possibilities where we can, 1, try to charge towards the slide. That's going to give, in 3 steps, we're going to end up 1, 2, 3. We're actually going to get -1 reward. So that's not our best action. Our best action is just to stay in place. And because the value is equal to the maximum of all our possible actions, our best is going to be 0. For E, it's slightly more different. If we have 3 actions, we can go down the water slide once, and then end up in a no reward situation, which is much better than just going down and not getting any reward. So our best possible outcome here is where we slide down the slide. That's 4. So now that we have a bit of intuition, let's take a look at if we had 10 steps into the future. So 10 steps, obviously, if we're in state A, we want to go down the slide. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or we'll never make it back around 1. We have to use 2 reward to go up the slide, and then we gain 4. So this is going to give us 2. For E, we're actually never going to make it back around either. So this is going to just give us 4. Now, we consider situations where we have a discount factor, where we want to go down the slope. We want to gain reward as soon as possible. So if we have 0.1, then let's first look at E. Our best possible action is still to go down the slide. Nothing changed there. We go down once, we get 2 reward at the closest one. But for the next one, we're going to have slightly less happiness. That's going to be gamma times 2, which in our case, gamma is 0.1. This is going to be 0.2. So this is going to give us a final result of 2.2. Now A is a little more complicated. So in one case, we can just stay in place. That's going to be 0. It's 0 reward ever. Or we can try going down the slide. If we try to go down the slide, we have 1, 2, 3 actions to get before we get a negative reward. So it's going to be 0.1 to the 3rd power times -1 plus 0.1 to the 4th power times -1 as well. And then finally we can get a positive reward. This is 0.1 to the 5th power times +2. Similarly, we have 0.1 to the 6th power plus +2. So now that we have this situation, we realize that the better action is actually just to stay in place, because this value is negative. So our value here is just 0. Now we consider Q values. Obviously, if we're in A, we can't go west, so we don't need to consider those. If we're in east, what is the best that we can do if we only had 1 step and we can only go west? Nothing. We just go west and get no reward. That's simple. But what if we're in east? We can go west, but we get 10 steps. So our best course of action is to go off and then immediately try to get the best we can get. So we're going to spend 1 to get off, and then afterwards we're going to try to get as much reward as possible. So it's minus, this is down here, -1 plus 2 plus 2. This is going to give us 3. Now let's take into consideration the pure value given a certain gamma. So this means that if we are given infinite time steps, so if we have infinite time steps, we never get any discount. Gamma is 1. Then in this situation, we can just loop around. In both states, we can just loop out around for infinity and just get as much reward as we want. So this is infinity in both states. What becomes slightly stranger is if we have actually a discount factor of 0.1. Once we have 0.1, we become more prone to getting the things that are closer to us and less so the ones that are further. The same math applies as with the 10-step case. Because when we go around, we're going to at each point in time get a negative reward. So A actually does not really want to move. A just doesn't want to approach the slide. So it will get 0 reward, even at infinity. Similarly for E, once we go down, we get that first time reward, but we never want to touch climbing up the slide ever again. So this is going to give us the same value, 2.22.